All right, team, gather round. Today we're tackling one of the most fundamental decisions you'll ever make as a digital design engineer. We're talking about choosing a logic family. Get this right and your design sings. Get it wrong, and well, you're in for a world of pain. So let's get into it. Every single piece of digital hardware you can think of, from a simple smartwatch to a massive supercomputer, is built from the ground up with logic gates. And that means the very first choice, the most critical decision you have to make, is picking the right kind of gate, the right logic family. It's the foundation of everything that comes after.
So, what is a logic family? The best way to think about it is like having different toolkits on your workbench. Each toolkit has the basics, your ands, your ors, your nots, but they're all built using different parts and principles. Each one has its own pros and cons, its own strengths and weaknesses. And our job, as engineers, is to pick the perfect toolkit for the job. And believe me, you've got options. I mean, look at this list. You've got the real old-school pioneers, like diode logic and resistor-transistor logic. Then you have the absolute workhorse of the 70s and 80s, TTL. And of course, you've got the modern champions like CMOS, which, let's be honest, is probably powering the device you're watching this on right now. We're not going to dissect every single one today, but you need to know what's out there.
Okay, so with a list that long, where do you even begin? Well, the first big fork in the road, the first major decision, splits the entire world of logic into two camps, bipolar and unipolar. And this choice has a huge impact on pretty much everything, speed, power, you name it.
So what's the difference? Well, bipolar families, like your classic TTL, are built with a mix of components, resistors, diodes, and those bipolar junction transistors. They're typically fast, they're tough, but man, they can be power hungry. Think of them like a muscle car. Then you have the unipolar families, like CMOS, which are built using only one type of component, MOSFETs. This lets you pack an insane number of them into a tiny space and use way less power. That's why they're everywhere today.
All right, let's say your project needs the speed and power of a bipolar family. You're not done choosing yet. Nope. There's another critical decision you have to make, and it's almost always a classic engineering trade-off between speed and, well, let's see. And here it is. It's all about how you drive the transistors. In saturated logic, think standard TTL. You're pushing that transistor all the way on. It's like flipping a light switch until it clicks. You get a really solid, definite on state, but it takes a little extra time to get it to turn back off. On the flip side, in non-saturated logic, like ECL, you never fully slam the switch on. You operate it in that middle region, and because of that, you can switch it on and off way, way faster. This is for when every nanosecond counts.
Now, all this theory is great, but to really understand these trade-offs, we've got to get our hands dirty. So we're going to put the simplest, most basic logic family on our virtual test bench, diode logic, or DL. We're going to see what makes it work, and more importantly, we're going to see where it fails, miserably.
The big selling point for diode logic is just how simple it is. I mean, you only need diodes and resistors. That's it. It's elegant. But that simplicity is also a huge weakness. You can only build OR gates and AND gates. You can't even make a simple NOT gate, an inverter, which is a massive, massive limitation for any real circuit.
So let's start with the OR gate. It seriously doesn't get much simpler than this. You've got two diodes for your inputs A and B, and a resistor pulling the output down to ground. The logic is simple. If input A times OR input B goes high, the diode turns on, and the output C gets pulled high. Easy. But pay very close attention to the actual voltages here. Look at that second row. We put in 5 volts for our logic 1 on input B, but what comes out at C? Only 4.3 volts. Why? Because you always get about a 0.7 volt drop across a standard diode. Now, that might not sound like a huge deal, but trust me, that little drop is the Achilles heel of this entire logic family. Okay, so that's the OR gate. Now let's look at its counterpart, the AND gate. You can see the circuit is basically flipped. We have a resistor pulling the output up to 5 volts, and the diodes are facing the other way. For this AND gate, the resistor wants to keep the output C high. But if either input A or B goes low, to 0 volts, that diode will turn on and yank the output voltage down to about 0.7 volts. That's our logic 0. The only possible way for the output to stay high is if input A and input B are both high, which keeps both diodes turned off. Pretty clever for just a few simple parts.
So far, so good, right? The individual gates work. They're simple, they're cheap. You're probably sitting there thinking, hey, what's the problem? Well, now we get to the fun part. Now we're going to do what all good engineers do. push it until it breaks.
See, in the real world, you never use just one gate in isolation. Real circuits are all about connecting gates together. The output of one becomes the input of the next, and so on. This is called cascading. So what do you think happens when we try to cascade our elegant little diode logic gates?
Look at this. This right here is the scene of the crime. We've got 3 OR gates chained one after another. The output of the first one feeds an input of the second, and its output feeds the third. This is a super common basic structure you'll build all the time.
Now let's trace the signal. We feed a nice, clean logic 1, 5 volts, into the very first gate. We already know what comes out, 4.3 volts, thanks to that diode drop. Okay, now that 4.3 volts becomes the input to the second gate. What happens? We lose another 0.7 volts. We're down to 3.6 volts. That feeds the third gate, and boom, we lose another 0.7 volts. The analysis shows, in some cases, it can drop to 2.9 V, even 2.2 V. Our beautiful logic 1 is dying a slow death.
This effect has a name, and you need to burn it into your brain: voltage degradation. It is the single fatal flaw of diode logic. There is no amplification in the circuit, nothing to boost the signal back up. Every gate it passes through just saps a little more life out of it, until eventually your logic 1 looks an awful lot like a logic 0, and your whole circuit just stops working.
So diode logic's failure is actually an incredible lesson. It teaches us that digital logic isn't just about abstract ones and zeros. It's about maintaining the physical analog integrity of the voltages that represent those ones and zeros. So I'm going to leave you with this question. How do you fix it? What single component could you add to these gates to not just perform logic, but to act like a little amplifier, restoring that signal to its full strength at every single stage? Because the answer to that question, well, that's what led to every other successful logic family that powers our entire world. Think about it.